terrifying. Close your eyes for a moment. I want you to imagine something. Imagine you are standing on a beach late at night, far away from any city, far away from any light pollution, far away from anything that reminds you of civilization. The sand beneath your feet is cold. The ocean in front of you stretches out into absolute blackness, and above you, the sky is on fire with stars. Thousands of them. Millions of them. A river of light cutting across the heavens, the Milky Way itself arching over you like a bridge made of diamonds and dust. You have seen the night sky before, of course you have, but tonight something feels different. Tonight, for the first time, you are not just looking at pretty lights. Tonight, you are going to understand what those lights actually mean, and I promise you by the time we are done here today, you will never look at that sky the same way again. Because here is the thing that nobody tells you when you are growing up. Nobody tells you just how terrifyingly, incomprehensibly, absurdly, impossibly large the universe actually is. They give you cute little diagrams in school. They show you the solar system with the planets lined up in a neat little row. They tell you the sun is big, Jupiter's bigger in a different way, and the stars are far away. But they never, ever sit you down and say the words that would change your entire perspective on existence. They never say, "You are so small that the word small does not even begin to describe it. You are so small that if the entire observable universe were shrunk down to the size of Earth, you would not even be an atom. You would not even be a quark inside an atom. You would be a rounding error in the mathematics of a rounding error. You would, for all practical purposes, not exist at all. And that is just the observable universe, the part we can see, the part whose light has had time to reach us in the 13.8 billion years since the Big Bang. That observable universe, that sphere of space 93 billion light-years across, containing 2 trillion galaxies, each with hundreds of billions of stars, each of those stars potentially orbited by planets, that staggering mind-crushing volume of space and matter and energy and time, that is not the whole universe. That is not even close. That might not even be a rounding error compared to the actual, total, complete universe. And the James Webb Space Telescope, the most powerful eye humanity has ever opened to the cosmos, just confirmed this in the most chilling, most extraordinary, most humbling way imaginable. So today we are going on a journey, and I do not use that word lightly. This is not a casual stroll through some fun space facts. This is a deep, thorough, unflinching exploration of the true scale of reality. We are going to start with what we thought we knew. We are going to build our way up through the astonishing technology of the James Webb Space Telescope. We are going to examine its most groundbreaking discoveries, including the farthest galaxy ever seen by human eyes, a galaxy so ancient that its light has been traveling toward us since the universe was barely 2% of its current age. We are going to confront the crisis that is currently tearing cosmology apart, a crisis called the Hubble tension, where the universe appears to be expanding faster than the laws of physics say it should. We are going to dive into the terrifying reality that 95% of the universe is completely invisible to us, made of substances we call dark matter and dark energy, substances we can detect but cannot see, cannot touch, cannot taste, cannot understand, and yet they control the fate of everything that exists. We are going to push beyond the observable universe, into the realm of the total universe, and confront estimates that say the actual cosmos could be millions, billions, or even infinitely larger than everything we can see. We are going to explore the multiverse, eternal inflation, and the possibility that our entire universe, infinite as it may be, is just one bubble in an ocean of bubbles that stretches beyond comprehension. And finally, we are going to face the ultimate question. How does it all end? What is the fate of the universe? And what does our place in all of this actually mean? If you are the kind of person who lies awake at night thinking about the stars, if you are the kind of person who feels a shiver down your spine when you contemplate infinity, if you are the kind of person who wants to understand the deepest truths about the cosmos we inhabit, then this is for you. Settle in. Get comfortable. Because we are about to go deeper than you have ever gone before. And before we begin this cosmic odyssey, I have one request. If at any point during this journey your mind is blown, if at any point you learn something that makes you see reality differently, do me a favor. Hit that subscribe button. Hit that like button. And drop a comment telling me how big you think the universe is. I want to see your guesses. I want to see your thoughts. Because this is not just my journey, it is ours. Together, let us begin. To understand why what the James Webb Space Telescope discovered is so terrifying, we first need to understand what we thought we knew about the universe before Webb opened its golden eye. And to understand that, we need to go back. Way back. Not just decades or centuries, but thousands of years, to a time when humans first looked up at the sky and tried to make sense of what they saw. For most of human history, the universe was small, laughably, almost adorably small by our current understanding. The ancient Greeks, brilliant as they were in so many ways, believed that the earth sat at the center of everything. Ptolemy, the great astronomer of the 2nd century, constructed an elaborate model where the sun, the moon, the planets, and the stars all orbited around our little world on crystalline spheres nested inside one another like a cosmic Russian doll. The stars, in this model, were all fixed on a single sphere, the outermost one, spinning around Earth once per day. The universe, in Ptolemy's estimation, extended maybe a few thousand Earth radii in every direction. That was it. That was the entirety of creation. A cozy little cosmic living room with Earth sitting comfortably in the center armchair. This view persisted for over 1,000 years. The medieval European worldview adopted Ptolemy's model almost wholesale, wrapping it in religious significance. Earth was the center because humanity was the center. The stars were the boundary because God had placed a boundary. The universe was comprehensible because God had made it comprehensible. It was neat, it was tidy, it was wrong. The first real crack in this comfortable picture came in 1543, when Nicholas Copernicus published his revolutionary work on the revolutions of the celestial spheres, proposing that the sun, not the earth, was at the center. Copernicus did not destroy the small universe, he simply rearranged it, but his idea planted a seed that would eventually grow into the most terrifying realization in all of science. If Earth is not the center, then maybe nothing is the center, and if nothing is the center, then maybe the universe is not a tidy little room. Maybe it is something much, much larger. Then came Galileo Galilei. In 1609, Galileo pointed a telescope at the night sky for the first time in history. What he saw changed everything. He saw craters on the moon, revealing it was not a perfect, smooth celestial sphere, but a world with mountains and valleys, like Earth. He saw the moons of Jupiter, 4 tiny points of light orbiting a planet that was not Earth, proving that not everything revolved around us. He saw the phases of Venus, which could only be explained if Venus orbited the Sun, not Earth. And he saw that the Milky Way, that hazy band of light across the sky, was not a cloud or a smear, but was made of individual stars, so many stars, packed so closely together that they blurred into a continuous glow. The universe had just gotten bigger, much bigger. But Galileo had no idea how much bigger it truly was. For the next 200 years, astronomers gradually expanded the map. They measured the distances to nearby stars using a technique called parallax, which involves observing how a star appears to shift position as Earth orbits the Sun, similar to how your thumb appears to jump left and right when you close one eye and then the other. The results were staggering. Even the nearest stars were light years away, meaning their light took years to reach us, traveling at 300,000 kilometers per second. The star Alpha Centauri, the closest star system to our Sun, turned out to be about 4.3 light years away. That is roughly 40 trillion kilometers. 40 trillion. And that is just the nearest neighbor. By the late 1700s, William Herschel had begun mapping the shape of the Milky Way, counting stars in different directions, and concluding that our galaxy was a flattened disk of stars with the Sun somewhere inside it. He estimated the galaxy was perhaps a few thousand light years across. He was off by a factor of about 30, but he was making progress. More importantly, he was the first to seriously consider that some of the fuzzy patches of light in the sky, the so-called nebulae, might be what he called island universes, separate collections of stars far beyond our own galaxy. But this idea was controversial. Many astronomers believed that the Milky Way was the entire universe, that those fuzzy nebulae were simply clouds of gas within our galaxy, and that nothing existed beyond. This debate raged for over a century, culminating in what is known as the Great Debate of 1920. On one side was Harlow Shapley, who argued that the Milky Way was enormous, perhaps 300,000 light-years across, and constituted the whole universe. On the other side was Heber Curtis, who argued that the Milky Way was smaller, but that those spiral nebulae were separate galaxies, island universes lying millions of light-years beyond our own. The debate was fierce, intellectual, and ultimately it would be settled not by arguments but by evidence. And that evidence came from one man, working alone at a telescope on a mountain in California. Edwin Hubble. The name itself has become synonymous with the expansion of human knowledge about the cosmos. In 1924, Hubble used the 100-inch telescope at Mount Wilson Observatory to observe a type of star called a Cepheid variable in the Andromeda Nebula. Cepheid variables are stars that pulsate in brightness in a very regular, predictable pattern. And crucially, the period of their pulsation is directly related to their intrinsic luminosity. This means that by measuring how long it takes a cepheid to go from bright to dim and back again, you can calculate how bright it actually is. Then, by comparing that true brightness to how bright it appears from Earth, you can calculate its distance. It is like knowing that a flashlight has a fixed brightness, and if it looks dim, it must be far away. When Hubble calculated the distance to the Cepheid in Andromeda, the result was shocking. It was approximately 900,000 light-years away. This was far beyond the bounds of the Milky Way, no matter how large you thought the Milky Way was. The implication was undeniable. Andromeda was not a nebula within our galaxy. It was a separate galaxy entirely. The Milky Way was not the universe. It was just one galaxy among many, possibly among billions. The universe had just exploded in scale, and the old cozy cosmic living room was gone forever, replaced by a vast, dark, terrifying ocean of space, populated by countless island universes stretching in every direction as far as telescopes could see. And even that was just the beginning, because Hubble did not stop there. In 1929, he made an even more startling discovery. He noticed that almost every galaxy he observed was moving away from us. And not just moving away, but moving away faster the farther it was. Galaxies twice as far away were receding twice as fast. Galaxies 3 times as far were receding 3 times as fast. This was not because we were at the center and everything was flying away from us. It was because space itself was expanding. Every point in space was moving away from every other point, like dots on the surface of a balloon being inflated. The galaxies were not flying through space. Space itself was stretching, carrying the galaxies along for the ride. This discovery, known as Hubble's law, was one of the most profound realizations in the history of science. If the universe is expanding now, then if you run the clock backward, everything was closer together in the past. Run it far enough back, and everything was in the same place. Infinitely dense, infinitely hot, compressed into a single point of unimaginable energy. And then, approximately 13.8 billion years ago, that point began to expand. Not an explosion into existing space, but an expansion of space itself. The Big Bang, the birth of the universe. So by the mid-20th century, humanity had gone from a cozy little geocentric universe that extended maybe a few thousand Earth radii to a universe that was billions of light years across, filled with billions of galaxies, and expanding in every direction. It was an incredible intellectual journey, and you might think that by that point we had a pretty good handle on how big the universe was. But you would be wrong, because the story was about to get much, much stranger. In 1965, two radio astronomers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were trying to use a large horn-shaped antenna for satellite communication experiments, but they kept picking up a persistent low-level hiss of microwave radiation. It was coming from every direction. It did not change with the time of day or the season. They checked their equipment. They cleaned the antenna. They even removed pigeon droppings from inside the horn, thinking the bird waste might be causing the noise. Nothing worked. The hiss persisted. Eventually, they realized that what they were hearing was not noise at all. It was the afterglow of the Big Bang itself, the cosmic microwave background radiation, or CMB. The CMB is, without exaggeration, one of the most important discoveries in the history of science. It is the oldest light in the universe, emitted approximately 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and photons to travel freely through space for the first time. Before that moment, the universe was an opaque, searing hot plasma, so dense and energetic that photons could not travel more than a short distance before being absorbed and re-emitted. But when atoms formed, the universe became transparent, and light was free to stream across space. That light has been traveling ever since, for over 13 billion years, and it has been stretched by the expansion of space from its original high-energy visible and infrared form into low-energy microwave radiation. It fills the entire sky. It comes from every direction equally. It is literally the baby photo of the universe, a snapshot of what the cosmos looked like when it was barely an infant, and it tells us extraordinary things. The CMB tells us that the universe is 13.8 billion years old. It tells us that the early universe was astonishingly uniform, with temperatures varying by only about 1 part in 100,000 across the entire sky. Those tiny temperature fluctuations, though, were the seeds of everything. The slightly denser regions had slightly more gravity, which attracted more matter, which made them denser still, which attracted even more matter. And over hundreds of millions of years, those tiny ripples grew into the galaxies, galaxy clusters, and vast cosmic structures we see today. Every galaxy, every star, every planet, every person alive today can trace their origin back to those infinitesimal variations in the temperature of the CMB. But the CMB also tells us something crucial about the size of the universe, something that directly sets the stage for what the James Webb Space Telescope discovered. The CMB is like a wall, a wall of light. We can see it in every direction, and it represents the farthest back in time we can look using electromagnetic radiation. Beyond the CMB, before 380,000 years after the Big Bang, the universe was opaque. Light could not travel freely, so we literally cannot see beyond that point. The CMB represents the edge of the observable universe, the boundary of everything we can detect with light-based telescopes. And that boundary tells us something astonishing about the size of the observable universe. You might think that since the universe is 13.8 billion years old, the observable universe should extend 13.8 billion light-years in every direction. After all, light travels at 1 light-year per year, so in 13.8 billion years, it should have traveled 13.8 billion light-years. Simple math, right? Wrong. This is one of the most common and one of the most important misconceptions in all of science, and understanding why it is wrong is absolutely critical to understanding the true scale of the cosmos. The key is that the universe has been expanding the entire time that light has been traveling through it. When light left a distant galaxy 13 billion years ago, that galaxy was much closer to us than it is now. But during those 13 billion years, space has been stretching. The galaxy has been carried farther and farther away by the expansion of space, and the light itself has been traveling through expanding space, covering more ground than it would have in a static universe. The result is that the most distant objects we can see are now much farther away than 13.8 billion light-years. They are approximately 46.5 billion light-years away, in every direction. So, the observable universe is a sphere with a radius of approximately 46.5 billion light-years, giving it a diameter of about 93 billion light-years. 93 billion light-years. Let me try to put that in perspective for you, even though I know that truly grasping this number is essentially impossible for the human mind, which evolved to understand distances measured in footsteps and throwing ranges, not in billions of light-years. 1 light-year is the distance light travels in 1 year, moving at approximately 300,000 kilometers per second. That works out to about 9.5 trillion kilometers. 1 light-year is 9.5 trillion kilometers. The nearest star to our Sun, Proxima Centauri, is about 4.2 light-years away, or roughly 40 trillion kilometers. If you could drive a car at the highway speed, 100 kilometers per hour, 24 hours a day, 7 days a week, without stopping, it would take you about 45 million years to reach Proxima Centauri. 45 million years in a car to reach the nearest star, and our galaxy, the Milky Way, is about 100,000 light-years across, and the observable universe is 93 billion light-years across. That is 930,000 times the diameter of our entire galaxy. If the Milky Way were the size of a dinner plate, the observable universe would be a sphere nearly 200 kilometers in diameter. And within that sphere, the numbers are equally staggering. The observable universe contains an estimated 2 trillion galaxies. 2 trillion. And that is 2 million million. 2,000 billion. Each of those galaxies contains, on average, about 100 billion to 400 billion stars. So the total number of stars in the observable universe is something in the range of 700 sextillion. That is a 7 followed by 23 zeros. 700 quintillion. If you tried to count all the stars in the observable universe, 1 per second, it would take you about 22 trillion years. The universe itself is only 13.8 billion years old. You would need roughly 1,600 times the current age of the universe just to count the stars. And each of those stars potentially has planets. We now know, thanks to missions like NASA's Kepler telescope, that most stars in the Milky Way have at least one planet. Many have several. Extrapolating to the entire observable universe, we are looking at potentially hundreds of sextillions of planets. Worlds we have never seen, worlds we will never see, worlds where right now, at this very moment, alien sunsets might be painting alien skies in colors we do not have names for. Or worlds that are dead and barren, frozen wastelands or scorching hellscapes, orbiting their parent stars in eternal silence. We do not know. And that uncertainty, that incomprehensible scale combined with that absolute mystery, is a large part of what makes the universe so terrifying. But here is the crucial point, the point that sets up everything we are about to discuss regarding the James Webb Space Telescope. The observable universe, as incomprehensibly vast as it is almost certainly not the entire universe. It is just the part whose light has had time to reach us. The observable universe has an edge, a cosmic horizon, beyond which we cannot see. But there's no reason to think that the universe stops at that horizon. In fact, every piece of evidence we have suggests that it continues far, far beyond, in every direction, with more galaxies, more stars, more planets, more space, extending outward and outward and outward. The question is, how far does it go? How much more universe is there beyond what we can see? And for decades, that question was essentially unanswerable. We could see to the horizon, but we could not see past it. It was like being in the middle of an ocean, able to see to the horizon in every direction, but with no way of knowing whether the ocean extended for another mile or another million miles beyond that. And then we built something extraordinary, something that had been dreamed about for decades, worked on for a quarter of a century, that cost $10 billion, that involved 10,000 people from 14 countries, that had 344 individual points of potential failure during its deployment, any single one of which would have killed the entire mission. We built the James Webb Space Telescope. And on Christmas Day 2021, we launched it into space. And when it opened its golden eye and peered deeper into the cosmos than any instrument in human history, what it saw did not just surprise us. It terrified us. The James Webb Space Telescope, known as JWST, or simply Webb, is not just a telescope. It is the most complex, most expensive, and most powerful scientific instrument ever constructed by the human species. To understand why what it discovered is so significant, you need to understand what it is, how it works, and why it can see things that no previous telescope could. The story of Webb begins in 1996 when NASA first started planning a successor to the legendary Hubble Space Telescope. Hubble, launched in 1990, had been an extraordinary success, giving us breathtaking images of distant galaxies, nebulae, and other cosmic phenomena. But Hubble had limitations. It observed primarily invisible and ultraviolet light, with some near-infrared capability. And for the science that astronomers most wanted to do, looking at the very first galaxies that formed after the Big Bang, observing the formation of stars and planetary systems, and studying the atmospheres of exoplanets, what was needed was a telescope that could see in the infrared. The reason for this is fundamental to the physics of the expanding universe. Remember how we discussed redshift? When light travels through expanding space, its wavelength gets stretched. Light that was emitted as ultraviolet or visible light by the first galaxies billions of years ago has been stretched by the expansion of space over those billions of years into infrared wavelengths by the time it reaches us. The most ancient, most distant light in the universe is infrared light. To see the very first galaxies, you need an infrared telescope. And not just any infrared telescope. You need one in space, above Earth's atmosphere, which absorbs most infrared radiation. You need one that is incredibly sensitive, with a mirror large enough to capture the unimaginably faint photons that have been traveling for over 13 billion years. And you need one that is so cold, so incredibly cold, that its own heat does not drown out the faint infrared signals from the distant universe. Building such a telescope was one of the most ambitious engineering challenges in human history. The original plan called for a launch in 2007 with a budget of about $1 billion. It ended up taking until 2021 and costing $10 billion. But the result was a marvel of human engineering unlike anything that had come before. The primary mirror of JWST is 6.5 meters across, made of 18 hexagonal segments of gold-coated beryllium. Gold is used because it is an excellent reflector of infrared light. Each segment is about the size of a coffee table, and together they form a mirror with about 6 times the light collecting area of Hubble's mirror. This means JWST can see objects that are roughly 100 times fainter than the faintest objects Hubble could detect. It is like going from looking at the night sky with a pair of binoculars to looking with the most powerful telescope ever built. But collecting more light is not enough. You also need to keep the telescope cold. Any warm object emits infrared radiation, and if the telescope itself is warm, its own emissions will overwhelm the faint infrared signals from distant galaxies. This is like trying to see a candle on a distant hillside while standing in front of a bonfire. To solve this problem, JWST has a sun shield, a 5-layer shield made of a material called Captain. Each layer thinner than a human hair but coated with aluminum and doped silicon to reflect sunlight and heat. When fully deployed, the sun shield is about the size of a tennis court. It sits between the telescope and the sun, blocking sunlight and allowing the telescope to cool to an operating temperature of about minus 233 degrees Celsius, just 40 degrees above absolute zero. At this temperature, the telescope's own infrared emissions are negligible, and it can detect the faintest whispers of infrared light from the edge of the observable universe. JWST does not orbit Earth like Hubble does. Instead, it orbits the Sun at a special location called the second Lagrange point, or L2, which is approximately 1.5 million kilometers from Earth, about 4 times the distance from Earth to the Moon. At L2, the gravitational pulls of the Earth and Sun, combined with the centripetal force of the orbit, create a stable point where JWST can maintain its position relative to Earth, while keeping its sun shield permanently oriented toward the Sun. This keeps the Sun, Earth, and Moon all on one side of the telescope, with the cold, dark universe on the other side. It is the perfect vantage point from which to observe the cosmos. One of the most nerve-wracking aspects of the Webb mission was its deployment. Unlike Hubble, which was placed in low Earth orbit and could be serviced by space shuttle astronauts when things went wrong, JWST at L2 is far beyond the reach of any crewed spacecraft. If something broke, there would be no way to fix it, and the deployment was extraordinarily complex. The telescope and its sun shield were too large to fit inside the rocket fairing of the Ariane 5 rocket that launched it, so they had to be folded up like origami for launch and then unfolded in space over the course of about 2 weeks. This unfolding involved 344 individual steps, each of which was a potential single point of failure. 1 stuck latch, 1 jammed motor, 1 misaligned hinge, and the entire $10 billion mission would have been dead. Every single step worked perfectly. When the mission control team in Baltimore confirmed that the final mirror segment had locked into place, there were tears in the control room. Decades of work, careers worth of effort, one of the greatest engineering achievements in human history, and it worked flawlessly. And then came the images. On July 12, 2022, the first full-color images from the James Webb Space Telescope were released to the world. They were unveiled by President Biden at the White House, and they took the world's breath away. The flagship image was called SMACS0723, Webb's first deep field. It showed a tiny patch of sky, an area roughly the size of a grain of sand, held at arm's length. If you stood outside and held a grain of sand at arm's length against the night sky, the area of sky covered by that grain of sand is what Webb imaged. And in that impossibly tiny patch of sky, Webb saw thousands of galaxies. Thousands. Some of them were relatively nearby, bright and detailed, their spiral arms and elliptical shapes clearly visible. Others were behind them, distorted into arcs and streaks by the gravity of a massive galaxy cluster in the foreground, a phenomenon called gravitational lensing, where the mass of the foreground cluster warps space itself, bending and magnifying the light of galaxies far behind it. And behind even those, the tiniest, faintest, reddest dots were some of the most distant galaxies ever seen, their light having traveled for over 13 billion years to reach Webb's mirror. We were looking at galaxies as they existed when the universe was less than 1 billion years old. The other images were equally stunning. The Carina Nebula, a region of active star formation about 7,600 light-years from Earth, was revealed in breathtaking detail. Webb's infrared eyes could peer through the clouds of dust that had hidden the innermost regions from Hubble, revealing hundreds of previously unknown young stars being born in towering walls of gas and dust that NASA described as looking like cosmic cliffs. Stephan's Quintet, a grouping of 5 galaxies in the constellation Pegasus, was shown in unprecedented detail, revealing shock waves, tidal tails, and bursts of star formation caused by the gravitational interactions between the galaxies. The Southern Ring Nebula, a shell of gas and dust blown off by a dying star, was revealed to have a complex structure that told a rich story of the star's final moments, including a previously unseen companion star. And the atmospheric spectrum of WASP-96b, a hot gas giant exoplanet about 1,150 light-years from Earth, showed clear evidence of water vapor in its atmosphere, marking the first time such a detailed atmospheric spectrum of an exoplanet had been obtained. These images were more than just pretty pictures. They were proof that JWST worked as designed, that it could see deeper, clearer, and farther into the infrared universe than anything that had come before. They were a down payment on the scientific revolution that was about to unfold. And that revolution, when it came, would challenge everything we thought we knew about the universe. Because when JWST turned its golden eye to the most distant reaches of the observable universe, to the first galaxies that formed in the cosmic dawn, what it found there was not what anyone expected. Let me take you to the edge of the observable universe, to a time so remote, so ancient that the numbers almost lose their meaning. Let me take you to a galaxy called MOM-Z14. Because this galaxy, a tiny faint smudge of light detected by the most powerful telescope ever built, has become one of the most important objects in the history of astronomy. And understanding why requires us to understand what the universe was like in its earliest moments. After the Big Bang, 13.8 billion years ago, the universe was unimaginably hot, dense, and uniform. In the first fraction of a second, the fundamental forces of nature separated from one another. Quarks combined to form protons and neutrons, and the basic building blocks of matter were established. In the first 3 minutes, protons and neutrons fused together to form the nuclei of the lightest elements, mainly hydrogen and helium, with trace amounts of lithium. But the universe was still so hot and dense that atoms could not form. Electrons were stripped away from nuclei almost as fast as they could combine. The universe was a searing plasma, opaque to light, like the interior of a star. This state persisted for about 380,000 years. Then, as the universe expanded and cooled, the temperature dropped below about 3,000 degrees Kelvin, cool enough for electrons to finally bind to nuclei and form neutral atoms. This event, known as recombination, had a dramatic consequence. With the free electrons now bound up in atoms, photons could travel freely through space for the first time. The universe went from opaque to transparent, almost like a fog suddenly lifting. The light released at that moment is what we now detect as the cosmic microwave background, the baby photo of the universe. But after recombination, something unexpected happened. Or rather, something did not happen for a very long time. No stars formed. The universe was filled with hydrogen and helium gas, slowly cooling, slowly spreading out, shrouded in darkness. There were no sources of light anywhere. No stars, no galaxies, no quasars, no anything. Just gas and dark matter, drifting in an expanding void. This period is known as the Cosmic Dark Ages, and it lasted for roughly 100 to 200 million years. It was the longest night in history, a period of absolute darkness that encompassed the entire universe. But within that darkness, something was stirring. The tiny fluctuations in density imprinted by the Big Bang, the same fluctuations visible in the CMB, were slowly growing under the pull of gravity. Regions that were slightly denser than average pulled in more gas. Dark matter, which makes up about 84% of all matter in the universe, played a crucial role here. Dark matter had already begun to clump together, forming what cosmologists call dark matter halos, vast, invisible structures of dark matter held together by gravity. These halos acted like gravitational wells, attracting ordinary hydrogen and helium gas into their centers. As the gas fell inward, it compressed, heated up, and eventually, in the densest clumps, ignited nuclear fusion. The first stars were born. These first stars, known as population 3 stars, were unlike any star that exists today. They were made of pure hydrogen and helium, with no heavier elements whatsoever, because no heavier elements existed yet. Heavier elements, things like carbon, oxygen, iron, the stuff that planets and people are made of, can only be created inside stars, through nuclear fusion, or in the violent deaths of stars, in supernovae. The first stars had none of these elements, and because of their pristine composition, theoretical models predict they were enormous, perhaps hundreds of times the mass of our Sun, burning with incredible ferocity and shining with a luminosity millions of times greater than our Sun. They burned through their fuel in just a few million years, far less than the 10 billion-year lifetime of a star like our Sun, and then they died in spectacular explosions, supernovae and hypernovae that scattered the first heavy elements into the surrounding gas, enriching it and making it possible for the next generation of stars, and eventually planets and life, to form. As more stars formed and gathered together under gravity, the first galaxies began to take shape. These were not the majestic spiral galaxies we see today. They were small, irregular clumps of stars, perhaps just a few million stars each, compared to the hundreds of billions in the Milky Way. But they were the seeds from which all future galaxies would grow, through mergers, accretion of gas, and billions of years of gravitational evolution. And these first stars and galaxies did something else of profound importance. Their intense ultraviolet radiation began to strip electrons from the neutral hydrogen gas that filled the universe, a process called reionization. The universe, which had become transparent at recombination, but then filled with neutral hydrogen that was opaque to ultraviolet light, was now being lit up again. this time by the stars themselves. The epoch of reionization, as it is called, was the moment the universe turned the lights on, transforming from a dark, neutral void into the transparent, ionized cosmos we see today. And it is precisely this epoch, this critical transition period in the history of the universe, that the James Webb Space Telescope was built to explore. Which brings us to MOM-Z14. On May 16, 2025, the NIR CAM instrument aboard the James Webb Space Telescope captured an image of a region of sky called the cosmos field. Among the countless galaxies in that image, astronomers identified a faint source of light that appeared to be extraordinarily distant. Follow-up spectroscopic observations confirmed its identity. The galaxy, designated MOM-Z14, has a cosmological redshift of 14.44. Let me explain what that number means, because it is one of the most extraordinary numbers in all of science. Redshift is the measure of how much the wavelength of light from an object has been stretched by the expansion of the universe. A redshift of 0 means no stretching. The object is right here. A redshift of 1 means the light's wavelength has been doubled. A redshift of 14.44 means the light's wavelength has been stretched by a factor of 15.44. That is, the light we are seeing from MOM-Z14 was emitted at a wavelength that has been stretched to more than 15 times its original length by the time it reached us. This degree of stretching corresponds to an extraordinary distance and an extraordinary look-back time. The light from MOM-Z14 has been traveling through expanding space for approximately 13.5 billion years. When that light was emitted, the universe was only about 280 million years old. 280 million years after the Big Bang. That is barely 2% of the universe's current age. If the entire history of the universe were compressed into a single calendar year, with the Big Bang at midnight on January 1st and the present day at midnight on December 31st, then MOM-Z14 existed on approximately January 7th. We are seeing this galaxy as it was in the first week of the cosmic year, and here is where the numbers get truly mind-bending. The light from MOM-Z14 was emitted 13.5 billion years ago, when the galaxy was relatively close to us, cosmically speaking. But during those 13.5 billion years, space has been expanding. The galaxy has been carried farther and farther away by the stretching of space itself. So, although the light took 13.5 billion years to reach us, MOM-Z14 is not 13.5 billion light-years away from us right now. It is much farther. Due to the cumulative expansion of space over those 13.5 billion years, MOM-Z14 is now approximately 33 billion light-years away from us. And that distance is increasing every second as the universe continues to expand. But what makes MOM-Z14 truly remarkable and truly unsettling is not just its distance. It is what it looks like, or rather, what it should not look like. Because according to our best models of the early universe, a galaxy existing just 280 million years after the Big Bang should be small, faint, and primitive. It should be a barely there collection of the very first stars, struggling to assemble in the cosmic darkness. It should be metal poor, because there had barely been enough time for any stars to live and die and scatter heavy elements into the surrounding gas. It should be, in a word, unimpressive. MOM-Z14 is none of these things. It is brighter, denser, and more chemically enriched than any model predicted for a galaxy of its age. It shows evidence of significant stellar populations, stars that have already been forming for some time, building up the galaxy's mass and enriching its gas with heavier elements through supernovae. Rohan Naidu, the astronomer at the Massachusetts Institute of Technology, who led the research team that discovered MOM-Z14, said in NASA's official announcement, "With Webb, we are able to see farther than humans ever have before, and it looks nothing like what we predicted, which is both challenging and exciting." Read that quote again. It looks nothing like what we predicted. This is not a minor discrepancy. This is not a small adjustment to existing models. This is a fundamental challenge to our understanding of how the early universe worked. MOM-Z14 exists at a time when the universe should barely have had enough time to form the first stars, let alone assemble them into a bright, chemically enriched galaxy. And yet, there it is, staring back at us from across 13.5 billion years of cosmic time, defying our expectations, challenging our theories, and telling us, in no uncertain terms, that the universe was doing something in its earliest moments that we do not yet understand. MOM-Z14 broke the previous record for the most distant galaxy ever confirmed, which was held by JADES-GS-Z14-0, a galaxy at redshift 14.32, discovered by JWST in May 2024, existing about 290 million years after the Big Bang. And before that, the record was held by other JWST discoveries that had been pushing the boundary deeper and deeper into cosmic history since the telescope began operations. Before JWST, the most distant confirmed galaxy was GN-Z11, discovered by Hubble at a redshift of about 11, corresponding to a time about 400 million years after the Big Bang. JWST has pushed that boundary by hundreds of millions of years closer to the Big Bang, deeper into the cosmic dark ages than anyone thought possible. And here is the truly exciting part. NASA has said that it fully expects MOM-Z14's record to be broken in the future, as JWST continues to observe deeper and more systematically. The telescope is still operating, still scanning, still pushing the boundaries of the observable universe. We may well find galaxies at redshifts of 15, 16, or even higher, galaxies that existed within the first 200 million years after the Big Bang, during the deepest depths of the cosmic dark ages. And each of those discoveries will teach us something new about how the universe came to be. But MOM-Z14 is not an isolated case. It is part of a much larger pattern of discoveries that JWST has made, a pattern that has sent shockwaves through the astrophysics community and has forced scientists to fundamentally reconsider their models of the early universe. Because MOM-Z14 is just the most extreme example of a phenomenon that JWST has been revealing since its very first deep observations. There are far more bright, massive, and mature galaxies in the early universe than anyone predicted, and this is a problem, a very big problem. When JWST began its systematic surveys of the distant universe in 2022 and 2023, the results were immediately striking. Everywhere it looked, JWST was finding galaxies in the early universe that were too numerous, too bright, and apparently too massive to fit the predictions of the standard cosmological model known as Lambda-CDM. Lambda-CDM is the best model we have for describing the large-scale structure and evolution of the universe. It incorporates general relativity, dark matter, dark energy, represented by the cosmological constant lambda, and our understanding of how structures form and grow over cosmic time. According to Lambda-CDM, the first galaxies should have been small and faint, building up slowly through mergers and gas accretion over hundreds of millions of years. The universe needed time to form stars, to build up galaxies, to create the massive structures we see today, or so we thought. JWST found otherwise. In 2023, a team of astronomers announced the discovery of 6 galaxies from when the universe was only 500 to 700 million years old that appeared to be staggeringly massive, potentially rivaling the mass of the Milky Way itself. This was deemed essentially impossible by the Standard Model. There simply was not enough time in those first few 100 million years for galaxies to accumulate that much mass through the normal processes of hierarchical assembly, where small galaxies merge to form bigger ones, which merge to form bigger ones still. The headlines were sensational. JWST discovers enormous distant galaxies that should not exist. Some scientists even suggested that these findings could break the lambda CDM model entirely. This was the era of what the astrophysics community came to call the impossible galaxies. And it was not just those 6. Across multiple surveys, JWST was consistently finding more galaxies in the early universe than predicted, and those galaxies were consistently brighter and apparently more massive than the models allowed. The Standard Model predicted a gradual buildup of structure, a slow dawn. JWST was showing something more like a sudden sunrise. But as with all great scientific puzzles, the story turned out to be more nuanced than the initial headlines suggested. As astronomers dug deeper into the data, they began to realize that some of the mass estimates for these early galaxies had been inflated by a subtle and unexpected contaminant in the data. Many of these early galaxies, it turned out, harbor supermassive black holes at their centers, black holes that are actively feeding on surrounding gas and emitting enormous amounts of radiation. These active galactic nuclei, or AGN, were contributing significant amounts of light to the galaxy's overall brightness, making the galaxies appear much more massive than they actually were. This population of objects became known as little red dots, compact, red sources in JWST's deep surveys. Their red color comes from the combination of cosmological redshift and dust reddening, and their compact size initially made them look like extremely massive galaxies. But spectroscopic follow-up revealed the telltale signatures of AGN activity, emission lines characteristic of gas being heated to extreme temperatures as it spirals into a black hole. When the AGN contribution was subtracted, many of these galaxies' masses dropped significantly. A study published in August 2024 was cheekily titled, "Webb finds early galaxies weren't too big for their britches after all." The conclusion was that while the early galaxies were indeed more numerous and slightly more massive than predicted, they were not so massive that they fundamentally broke the lambda CDM model. But the story does not end there, because even with the mass corrections, JWST is still seeing more galaxies in the early universe than predicted. The quote from NASA was telling, "We are still seeing more galaxies than predicted, although none of them are so massive that they break the universe." The lambda CDM model survives, but it survives on a life support machine, requiring significant adjustments to its parameters and predictions. The universe matured faster than we thought. Galaxies assembled more quickly. Star formation was more efficient in the early cosmos than our models allowed. And this raises profound questions about the physical processes at work in the first few 100 million years of cosmic history. And then there is the black hole problem, which is arguably even more disturbing than the galaxy problem. In January 2026, just weeks before I am telling you this story, JWST revealed a galaxy from when the universe was only 470 million years old that contains a supermassive black hole with an estimated mass of 40 million suns. 40 million times the mass of our sun, packed into a single black hole, just 470 million years after the Big Bang. Scientists describe this finding as a real revolution in our understanding of how black holes form and grow. Because according to our standard understanding, supermassive black holes are built gradually. A massive star dies, forming a stellar mass black hole of perhaps 10 to 100 solar masses. That black hole then grows by accreting surrounding gas and by merging with other black holes over billions of years. But there is a physical limit to how fast a black hole can grow by accreting gas, known as the Eddington limit, which is determined by the balance between the inward pull of gravity and the outward push of radiation pressure from the infalling gas. Even at the maximum Eddington rate, it takes a very long time to grow a black hole from 10 solar masses to 40 million solar masses, more time than was available in the first 470 million years of the universe. So, how did these supermassive black holes get so big so fast? There are several possibilities being actively debated. One is that the first black holes did not start as stellar mass objects at all. Instead, they may have formed through the direct collapse of massive clouds of primordial gas, bypassing the star formation stage entirely and creating seed black holes that were already thousands or tens of thousands of solar masses from the start. Another possibility is that the first black holes grew at rates exceeding the Eddington limit through a process called super-Eddington accretion, where gas falls in so fast that the radiation cannot escape quickly enough to push it back. A third possibility is that black holes in the early universe grew primarily through mergers, combining with each other in the dense environment of the first galaxy clusters. And a fourth, more radical possibility is that the physics of black hole growth is different at very high redshifts than it is in the local universe, perhaps due to the different conditions of the early cosmos, such as the higher density of gas, the lower metallicity, or the different background radiation field. JWST is not just finding these early supermassive black holes. It is finding them in numbers and at masses that challenge every model we have. And this, combined with the excess of bright galaxies, paints a picture of an early universe that was far more active, far more complex, and far more surprising than anyone anticipated. The universe, it seems, did not wait patiently for hundreds of millions of years before getting to work. It hit the ground running, and we do not yet fully understand how. Now, I want you to hold that thought. The thought that the early universe was more productive and more complex than we expected, because it has a direct bearing on the question of the total size of the universe. If galaxies formed faster and more efficiently than our models predicted, it means that the processes driving galaxy formation, primarily the gravitational collapse of dark matter halos and the accretion of gas, were more vigorous than we thought. And if those processes were more vigorous within the observable universe, they were almost certainly more vigorous everywhere else too, in the vast expanses of space beyond our cosmic horizon. More galaxies forming faster means more structure everywhere, which means the universe, in its totality, may be even richer and more populated than our previous estimates suggested. But the impossible galaxies and the early supermassive black holes are not the only crisis JWST has thrust upon the world of cosmology. There is another, even more fundamental problem, one that strikes at the very heart of our understanding of how the universe works. It is called the Hubble tension, and it has been described as the most important unsolved problem in cosmology, and JWST, rather than resolving it, has made it worse, much worse. If you want to support this kind of deep, thorough exploration of the cosmos, now is the moment. Tap that like button, subscribe to the channel, share this video with a friend who loves space, and drop a comment telling me what you think is causing the Hubble tension, because we are about to dive deep into one of the greatest mysteries in all of physics, the Hubble tension. Even the name sounds ominous. A tension at the heart of cosmology, a discrepancy that will not go away no matter how hard we try to make it. A crack in the foundation of our understanding of the universe that threatens to bring the whole edifice crashing down. Let me explain what it is, why it matters, and why JWST has made it a full-blown crisis. At its core, the Hubble tension is a disagreement between two measurements of the same number, the Hubble constant, denoted h0 or h0. The Hubble constant is one of the most fundamental numbers in all of cosmology. It tells you how fast the universe is expanding right now. Specifically, it tells you how fast a galaxy is moving away from us for every megaparsec of distance between us and that galaxy. A megaparsec is about 3.26 million light-years. So if h0 is, say, 70 kilometers per second per megaparsec, that means a galaxy 3.26 million light-years away is moving away from us at 70 kilometers per second. A galaxy twice as far is moving away at 140 kilometers per second, and so on. The bigger the distance, the faster the recession, because more space means more expansion. Knowing h0 is crucially important because it determines the age of the universe, the size of the observable universe, the density of matter and energy in the cosmos, and ultimately the fate of everything that exists. Get h0 wrong, and your entire picture of cosmology is wrong. So, measuring it accurately is one of the highest priorities in all of physics. And for decades, two different methods of measuring h0 have been giving two different answers, and neither one is wrong. The first method uses the cosmic microwave background. As we discussed earlier, the CMB is the afterglow of the Big Bang, light from when the universe was just 380,000 years old. The tiny temperature fluctuations in the CMB encode an enormous amount of information about the early universe, including its density, composition, and geometry. By feeding these measurements into the lambda-CDM model, the standard model of cosmology, physicists can calculate what the expansion rate of the universe should be today, 13.8 billion years later. The most precise CMB measurements come from the European Space Agency's Planck satellite, which mapped the CMB from 2009 to 2013 with extraordinary accuracy. The result? h0 equals approximately 67.4 kilometers per second per megaparsec. This is the early universe prediction. The second method measures the expansion rate directly by looking at objects in the relatively nearby universe and measuring both their distances and their recession velocities. The technique relies on what is called the cosmic distance ladder. First, you measure the distances to nearby Cepheid variable stars using parallax. Then, because you know the relationship between a Cepheid's pulsation period and its intrinsic brightness, you can use Cepheids in more distant galaxies to measure those galaxies' distances. Then, in those galaxies, you observe Type 1a supernovae, which are a special class of exploding star that always reaches roughly the same peak brightness, making them excellent standard candles for measuring even greater distances. By combining these distance measurements with the observed redshifts of the galaxies, which tell you how fast they are receding, you can calculate h0 directly from the local universe. The most precise local measurements come from the SHOES team, led by Nobel laureate Adam Rees. The result, h0 equals approximately 73.0 kilometers per second per megaparsec. This is the local universe measurement. 67.4 versus 73.0, a difference of about 8 or 9%. That might not sound like much. You might think, well, close enough, right? Wrong. Both measurements are incredibly precise. The error bars on each are small. The discrepancy between them is what physicists call a 5 sigma tension, meaning there is less than a 1 in a million chance that the disagreement is due to random measurement error. This is not a rounding error. This is not an instrumentation glitch. This is a fundamental inconsistency between two of the most carefully conducted measurements in the history of science. The early universe says the expansion rate is 67.4. The local universe says it is 73. They cannot both be right, and yet both measurements appear to be correct. For years, cosmologists hoped that the discrepancy was due to some subtle systematic error, some overlooked source of uncertainty in one or both measurements. Maybe the Cepheid distances were slightly off. Maybe there was some unknown source of dust that was dimming the supernovae, making them appear farther away than they really were. Maybe the Planck satellite had some tiny calibration issue. These were reasonable hopes, and testing them was one of the primary reasons the James Webb Space Telescope was built. And test them it did. In December 2024, JWST conducted its largest ever study of the cosmic distance ladder, using its infrared vision to observe Cepheid variable stars in galaxies where Hubble had struggled. The advantage of JWST's infrared capabilities is enormous. Infrared light is much less affected by dust than visible light, and JWST's exquisite angular resolution allows it to separate individual Cepheids in crowded stellar fields where Hubble saw only blurred blobs. If there were systematic errors in Hubble's Cepheid distance measurements, JWST would find them. The result was devastating for those who hoped the tension would go away. JWST confirmed the higher value. The local measurement of H0 was not wrong. The Cepheid distances were accurate. The tension is real. The universe is genuinely expanding faster than our best model of cosmology, calibrated on the CMB, says it should be. And this confirmation, rather than resolving the crisis, deepened it into what Scientific American, in an April 2025 article called "No Longer a Tension, but a Full-Blown Crisis." In December 2025, additional independent measurements from the Keck Observatory further deepened the crisis, finding results consistent with the higher local value and further strengthening the case that the discrepancy is not due to measurement errors in either method. And in February 2026, physicists at the University of Illinois and the University of Chicago developed a new, independent method to measure the expansion rate, and their results also showed the tension persists. The Hubble tension is not going away. If anything, it is getting worse. So, what does this mean? If both measurements are correct, then something about our fundamental model of the universe is wrong. The lambda-CDM model, which has been the gold standard of cosmology for over 2 decades, accurately predicts the CMB, the large-scale structure of the universe, the abundance of light elements, and a host of other observations. But it cannot simultaneously explain both the CMB value of H0 and the local value of H0. Something is missing, some piece of physics that we have not yet discovered, and the possibilities are mind-blowing. One possibility is that there was a form of energy in the early universe that we do not know about, sometimes called early dark energy. This would be a form of dark energy that was significant in the first few 100,000 years after the Big Bang, boosting the expansion rate during that period, but then rapidly decaying and becoming negligible. This would change the CMB predicted value of H0, potentially bringing it into agreement with the local measurement. But it would require a form of energy that our current physics does not predict, and whose origin and nature are completely unknown. Another possibility is that the properties of dark energy are not constant, but are changing over time. In the standard lambda-CDM model, dark energy is represented by the cosmological constant lambda, which has a fixed value that does not change. But what if dark energy is dynamic? What if its strength has been evolving over the history of the universe? Data from the Dark Energy Spectroscopic Instrument, or DESI, have provided tantalizing hints that this might be the case, suggesting that dark energy may have been weaker in the past and is getting stronger over time. If confirmed, this would be one of the most profound discoveries in the history of physics, because it would mean that the force driving the accelerating expansion of the universe is not a constant property of space itself, but a dynamic, evolving phenomenon whose nature we do not understand. A third possibility is that Einstein's theory of general relativity, the theory of gravity that underlies all of modern cosmology, needs to be modified at cosmological scales. General relativity has been tested with extraordinary precision in the solar system, in binary pulsars, and in gravitational wave observations, and it has passed every test. But it has never been directly tested at the scale of the entire observable universe. It is possible that gravity behaves differently at the very largest scales, in a way that affects the expansion rate. Modified gravity theories, such as MOND, modified Newtonian dynamics, or various F-registered gravity models, have been proposed, but none has yet provided a fully satisfactory resolution of the Hubble tension. A fourth possibility involves unknown particles. There might be particles that we have not yet detected, such as sterile neutrinos or some other form of dark radiation that contributed to the energy density of the early universe and affected the expansion rate. These particles would interact so weakly with ordinary matter that they would be essentially invisible to our current detectors, but their presence in the early universe would leave a subtle imprint on the CMB that could shift the predicted value of H0. A fifth, and perhaps most exotic possibility, is that we live in a cosmic void, a region of the universe that is slightly less dense than the average. In a void, the local expansion rate would be faster than the cosmic average, because there is less gravitational pull to slow it down. This could explain why the locally measured H0 is higher than the CMB prediction. However, the void would need to be extraordinarily large, hundreds of millions of light-years across, and there is no strong evidence for such a void in the distribution of galaxies around us. And there is always the sixth possibility, the most thrilling and most terrifying of all, that the answer is something completely new, something that no theorist has yet imagined, a fundamentally new aspect of physics that we have not conceived of. Every previous revolution in physics, from Newtonian gravity to Einsteinian relativity to quantum mechanics, came as a shock, upending the established worldview and replacing it with something stranger and more wonderful than anyone had anticipated. It is entirely possible that the resolution of the Hubble tension will require a similar revolution, a new understanding of the universe that is as far beyond our current comprehension as general relativity was beyond Newton. The Hubble tension matters for the question of the size of the universe because the Hubble constant directly determines the relationship between distance and recession speed. If the universe is expanding faster than we thought, then the observable universe is slightly different in size and age than we calculated, and more importantly, the total universe, the part beyond the observable, is expanding even faster than we realized, stretching the fabric of space at a rate that exceeds our current models. The universe is not just big, it is getting bigger, faster, and in a way that we do not fully understand, and that is deeply, profoundly unsettling. Now, let me take you even deeper, because the Hubble tension and the impossible galaxies, as disturbing as they are really just symptoms of a much larger, much more fundamental mystery. The mystery of the invisible universe. The mystery of the 95%. Because everything we have been talking about so far, every galaxy JWST has photographed, every star, every planet, every atom in your body, every photon in the CMB, all of that, every bit of it, makes up only 5% of the total content of the universe. 5%. The other 95% is made of two substances that we can detect but cannot see, cannot touch, cannot taste, and do not understand. They are called dark matter and dark energy, and together they are the real rulers of the cosmos. They determine the structure, the evolution, and the ultimate fate of everything that exists. And JWST, in January 2026, just gave us our most detailed look at one of them. Dark matter. Let us start with dark matter. The story of dark matter begins in 1933 with a Swiss-American astronomer named Fritz Zwicky. Zwicky was studying the Coma Cluster, a group of over 1,000 galaxies located about 320 million light-years from Earth. He measured the velocities of the galaxies within the cluster and calculated how much mass would be needed to gravitationally bind them, to keep them from flying apart. The answer stunned him. The galaxies were moving far too fast. Based on the visible mass of the cluster, the mass of the stars, and gas and dust that he could see, there was not nearly enough gravity to hold the cluster together. The galaxies should have been flying apart in all directions, but they were not. Something was holding them together, something invisible. Zwicky called this unseen substance dunkle materie, dark matter. For decades, Zwicky's observation was largely ignored. Dark matter seemed like a fringe idea, an ad hoc explanation for an anomaly that would probably go away with better measurements. But it did not go away. In the 1970s, astronomer Vera Rubin and her colleague Kent Ford made a discovery that brought dark matter roaring back to the forefront of physics. They measured the rotation curves of spiral galaxies. That is, how fast stars at different distances from the center of a galaxy are orbiting. In our solar system, the planets farther from the Sun orbit more slowly, because the Sun's gravitational pull weakens with distance. Rubin expected to see the same pattern in galaxies. Stars near the edge should orbit more slowly than stars near the center, but they did not. The rotation curves were flat. Stars at the edges of galaxies were orbiting just as fast as stars near the center. This was impossible unless there was a massive amount of invisible matter surrounding each galaxy in a vast spherical halo, extending far beyond the visible disk of stars. The halos had to contain several times more mass than all the visible matter in the galaxy combined. Since then, the evidence for dark matter has become overwhelming. It is seen in the rotation curves of galaxies. It is seen in the motions of galaxies within clusters. It is seen in the gravitational lensing of light from distant galaxies as it passes through intervening mass. It is imprinted in the cosmic microwave background, which tells us that dark matter makes up about 27% of the total energy content of the universe. It is required by the standard model of cosmology to explain the formation of the large-scale structure of the universe, the distribution of galaxies on the largest scales. Without dark matter, galaxies as we know them could not have formed. Stars could not have formed. Planets could not have formed. We could not have formed. Dark matter is not an optional add-on to our model of the universe. It is an essential, fundamental component without which the universe as we observe it would not exist. And yet, after nearly a century of searching, we still do not know what dark matter is. We know it has mass and therefore gravity. We know it does not emit, absorb, or reflect light. We know it does not interact with ordinary matter through the electromagnetic force. It appears to interact only through gravity and possibly through the weak nuclear force. Dozens of experiments around the world are searching for dark matter particles, from underground detectors buried deep beneath mountains to shield them from cosmic radiation, to particle accelerators like the Large Hadron Collider at CERN that try to create dark matter particles in high-energy collisions. So far, none of these experiments has produced a definitive detection. Dark matter remains, and one of the great ironies of science, the most abundant form of matter in the universe and one of the least understood. But what we do understand, thanks in part to JWST, is where dark matter is. In January 2026, NASA released the most detailed map of dark matter ever produced, created using data from the Cosmos Webb Survey, the largest contiguous imaging survey yet conducted by the James Webb Space Telescope. This map is an extraordinary achievement, and it tells us something profound about the architecture of the universe. The map was created using a technique called weak gravitational lensing. Gravitational lensing is a consequence of Einstein's general relativity. Massive objects warp the fabric of spacetime around them, and light passing through this warped spacetime follows a curved path. In the case of strong lensing, this produces dramatic arcs and multiple images of the background galaxies. But in weak lensing, the effect is much more subtle. A foreground mass, such as a concentration of dark matter, causes tiny distortions in the shapes of the background galaxies behind it, stretching them slightly in a coherent pattern. By measuring the shapes of hundreds of thousands of background galaxies and looking for these coherent distortions, astronomers can map the distribution of mass in the foreground, including the dark matter that is invisible to direct observation. The Cosmos Webb Survey imaged a patch of sky about 0.54 square degrees in area, roughly twice the apparent size of the full moon. In that tiny patch of sky, JWST detected nearly 800,000 galaxies, spanning over 13 billion years of cosmic history. By measuring the shapes of approximately 250,000 of those galaxies, the research team was able to construct the most detailed dark matter map ever produced. And what that map shows is breathtaking. The map reveals the cosmic web, the vast network of dark matter filaments that forms the underlying scaffolding of the universe. Galaxies are not distributed randomly through space. They are arranged along these filaments, strung like beads on an invisible cosmic necklace. The filaments converge at massive nodes, where galaxy clusters reside, enormous concentrations of thousands of galaxies held together by the gravity of equally enormous concentrations of dark matter. Between the filaments are vast, nearly empty voids, regions of space millions of light years across that contain almost nothing, just a sparse scattering of lonely galaxies. The JWST dark matter map shows this web in unprecedented detail, revealing how dark matter and ordinary matter overlap and intertwine. As NASA described it, the map shows the invisible scaffolding of the universe. The dark matter filaments are not just nearby, they extend to the very edges of the survey, to the most distant galaxies in the image, showing that the cosmic web has existed for most of the history of the universe. Dark matter began to form its web-like structure in the first few 100 million years after the Big Bang, and galaxies have been forming along those filaments ever since. The structure we see in the distribution of galaxies today is a direct reflection of the dark matter structure that was laid down billions of years ago. And here is what is so powerful about this map for our question about the size of the universe. The cosmic web extends to every boundary of the survey. There is no edge. There is no sign that the structure stops or thins out or changes character at the limits of what JWST can observe. The filaments run right up to the border of the image and clearly continue beyond. The dark matter web, the scaffolding of the universe, extends past the edges of our vision into the unobservable space beyond. And by extension, the galaxies that hang on that scaffolding also extend beyond our vision, galaxy after galaxy after galaxy, stretching outward in every direction, beyond the cosmic horizon, beyond the reach of any telescope, into the unknown. Now, let us talk about the other piece of the invisible universe, the even more mysterious piece, the piece that makes up not 27 but 68% of the total energy content of the cosmos. Dark energy. In 1998, two independent teams of astronomers made a discovery that would earn them the Nobel Prize in Physics and would fundamentally alter our understanding of the fate of the universe. One team, led by Saul Perlmutter, was the Supernova Cosmology Project. The other, led by Brian Schmidt and Adam Rees, the same Adam Rees who now leads the Hubble tension research, was the High-Z Supernova Search Team. Both teams were studying distant Type 1a supernovae, those standardizable exploding stars we mentioned earlier, to measure how the expansion of the universe was changing over time. The expectation was straightforward. The universe is full of matter, and matter has gravity. Gravity pulls things together. So the expansion of the universe, set in motion by the Big Bang, should be gradually slowing down as the mutual gravitational attraction of all the matter in the universe applies the brakes. The question was not whether the expansion was decelerating, but how fast. Was it decelerating slowly, meaning the universe would expand forever, but more and more slowly? Or was it decelerating quickly, meaning gravity would eventually halt the expansion and pull everything back together in a big crunch? The answer was neither. When both teams measured the distances and redshifts of distant Type 1a supernovae, they found something utterly unexpected. The supernovae were dimmer than they should have been if the expansion were decelerating. They were farther away than expected. The expansion of the universe was not slowing down at all. It was speeding up. The universe was accelerating. Something was pushing everything apart, overcoming the gravitational pull of all the matter in the universe and driving the expansion to ever greater speeds. They called this mysterious force dark energy. This was, and remains, one of the most shocking discoveries in the history of science. We live in a universe where the dominant form of energy, nearly 70% of the total, is something that pushes space apart, something that pervades every cubic centimeter of the vacuum, something that has no known source, no known mechanism, and no known explanation. The simplest theoretical explanation for dark energy is Einstein's cosmological constant, lambda, a fixed amount of energy inherent in space itself. Einstein originally introduced the cosmological constant in 1917 to make his equations of general relativity compatible with a static universe, but he later called it his greatest blunder when Hubble showed the universe was expanding. Now, ironically, it appears that Einstein may have been right after all, just for the wrong reasons. The cosmological constant might be real. Space itself might have an inherent energy that pushes it apart. But the cosmological constant has its own deep problem. When physicists try to calculate the expected value of the vacuum energy from quantum field theory, they get a number that is roughly 120 orders of magnitude larger than the observed value. 120 orders of magnitude. That is a 1 followed by 120 zeros. This is sometimes called the worst prediction in the history of physics. Something is canceling out almost all of the vacuum energy, leaving just a tiny residual amount that we observe as dark energy. No one knows what that something is. It is one of the deepest unsolved problems in fundamental physics. In January 2026, the results of the Dark Energy Survey, a 6-year observational campaign using a dedicated telescope in Chile to map the distribution and motions of hundreds of millions of galaxies, confirmed that the standard lambda-CDM model holds up, in the sense that the data are broadly consistent with a cosmological constant. But, and this is a very significant but, the data also showed hints that dark energy might not have always been constant. There are suggestions in the data that dark energy's effect only kicked in after a certain point in the universe's history, and that its strength may be changing over time. This is consistent with the earlier hints from D.E. Esang, which also found evidence for evolving dark energy. If dark energy is not constant but is instead dynamic, changing in strength over cosmic time, the implications are staggering. It would mean that the fate of the universe is not sealed. It could end in the gentle fading of the Big Freeze, or in the violent tearing of the Big Rip, or in some entirely new way that we cannot yet imagine, depending on how dark energy evolves in the future. It would mean that the expansion rate of the universe is not merely increasing, but increasing at a rate that itself is changing. And it would mean that the total size of the universe, past, present, and future, depends on the behavior of a force that we can measure but cannot explain. So, let me summarize where we stand. JWST has shown us galaxies that should not exist, forming too fast and too early in the universe's history. JWST has confirmed that the universe is expanding faster than our best model predicts, a crisis known as the Hubble tension. JWST has mapped the dark matter web, the invisible scaffolding of the universe, revealing that it extends to every limit of our observations with no sign of stopping. And dark energy, the mysterious force that makes up 68% of the cosmos, may be evolving over time, with implications we cannot yet fathom. Each of these discoveries, individually, would be groundbreaking. Together, they paint a picture of a universe that is stranger, larger, and more mysterious than we ever imagined. And now, armed with all of this knowledge, we can finally address the central question of this entire journey. How big is the universe? Not the observable universe, the actual, total, complete universe. Everything that exists. The answer, or rather, the range of possible answers, is where this story becomes truly terrifying. The observable universe, as we have established, is a sphere approximately 93 billion light-years in diameter, centered on Earth, not because Earth is special, but because it is our vantage point. The observable universe contains roughly 2 trillion galaxies, 100 sextillion stars, and an unimaginable number of planets, moons, asteroids, comets, and other objects. It is, by any human measure, incomprehensibly large. But the observable universe is not the whole story. It is merely the part of the universe whose light has had time to reach us. Beyond the cosmic horizon, beyond the boundary of the observable universe, there is more. The question is, how much more? To answer this, we need to consider the geometry of the universe, and here we enter the realm of one of the most profound results in all of cosmology. The geometry of the universe, its curvature, tells us about its overall shape and, potentially, its size. There are 3 possibilities. First, the universe could be positively curved, like the surface of a sphere. In a positively curved universe, if you traveled in a straight line far enough, you would eventually come back to where you started, like circumnavigating a globe. Such a universe would be finite in size but without an edge, just as the surface of a sphere is finite but has no boundary. In a positively curved universe, the total volume would be calculable from the radius of curvature. Second, the universe could be negatively curved, like a saddle or a Pringle chip. In a negatively curved universe, the geometry is hyperbolic. Parallel lines diverge, and the universe extends infinitely in all directions. Such a universe would be infinite in size. Third, the universe could be flat, with zero curvature, like a sheet of paper extending infinitely in all directions, but in 3 dimensions. In a flat universe, the geometry is Euclidean. Parallel lines stay parallel forever, and the universe also extends infinitely in all directions. A flat universe is also infinite in size. The measurements of the CMB by the Planck satellite have given us an extraordinarily precise measurement of the curvature of the universe. And the result is, the universe is flat. Or, more precisely, the curvature of the universe is consistent with 0 to within about 0.4%. The universe, as far as we can measure, is perfectly flat. This has profound implications. If the universe is perfectly flat, it is infinite. It extends forever in every direction, with no edge, no boundary, no end. There are galaxies beyond our cosmic horizon, and beyond those galaxies there are more galaxies, and beyond those more, and on, without limit, forever. But what if the universe is not perfectly flat, but just very, very close to flat? What if there is a tiny positive curvature that is too small for our instruments to detect? In that case, the universe would be finite but extraordinarily large. How large? The constraint from Planck's measurements is that if the universe has a slight positive curvature, its radius of curvature must be at least about 250 times the radius of the observable universe. That means the total universe, if finite, must have a volume at least 250 cubed, or about 15 million times the volume of the observable universe. And that is the absolute minimum. Other estimates, based on different analyses of the CMB data and on inflationary theory, suggest the universe could be 10 to the 23 times larger than the observable universe, or even more. 10 to the 23 is 100 sextillion. 100 sextillion times the volume of the observable universe. Let me try to put that in perspective. Imagine that the observable universe, that 93 billion light-year sphere containing 2 trillion galaxies and 100 sextillion stars, imagine that we shrunk it down to the size of a single atom, a hydrogen atom, about 1/10 billionth of a meter across. In this thought experiment, the observable universe is an atom. How big would the total universe be at the 10 to the 23 estimate? It would be approximately the size of the observable universe. Let me say that again, because I need you to really absorb this. If the observable universe were an atom, the total universe would be the size of the observable universe. We are comparing an atom to a sphere 93 billion light-years across, and the total universe might be even larger than that. This is what I mean when I say the true size of the universe is terrifying. It is not that the universe is merely big. Big is what you say about a mountain, or an ocean, or a galaxy. The universe is something else entirely. It is a scale so far beyond human comprehension that our language does not even have words for it. It is so large that the observable universe, the vast, staggering, mind-crushing sphere of 93 billion light-years that contains 2 trillion galaxies, and everything we have ever known or seen or measured, is an insignificant speck, a rounding error, a mote of dust, an atom, in a cosmos that may stretch forever. And the James Webb Space Telescope has brought us face to face with this reality in a way that no previous instrument has. By showing us the most distant galaxy ever seen, a galaxy that exists at the very edge of the observable universe, JWST has shown us the boundary, the wall, the limit beyond which we cannot see. And by confirming the Hubble tension, by mapping the dark matter web, by revealing the impossible galaxies, JWST has shown us that the universe beyond that wall is not empty. It is full of galaxies, full of stars, full of dark matter filaments, full of dark energy, full of structure and complexity and mystery, extending outward and outward and outward, perhaps forever, into a cosmos so vast that the human mind recoils from the attempt to comprehend it. But we do not stop there, because even if the universe is infinite or merely unimaginably vast, there is a further level of mind-breaking possibility that we must confront. The possibility that our universe, infinite as it may be, is not the only one. The possibility that there are other universes, perhaps infinitely many, each with its own laws of physics, its own history, its own galaxies and stars and planets, and perhaps its own forms of life. The possibility of the multiverse. And while this might sound like pure science fiction, it is actually a natural consequence of some of the most well-established and well-tested theories in modern physics. The multiverse idea emerges most naturally from the theory of cosmic inflation. Inflation, proposed by physicist Alan Guth in 1981, is the idea that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of extraordinarily rapid expansion, doubling in size many times over in less than a trillionth of a trillionth of a trillionth of a second. Inflation was not proposed as a speculative idea, but as a solution to several deep problems in cosmology. The horizon problem, why the CMB has the same temperature in every direction, even in regions that should never have been in causal contact. The flatness problem, why the universe is so close to geometrically flat. And the monopole problem, why we do not see magnetic monopoles, which many theories predict should have been produced in the early universe. Inflation solved all of these problems elegantly, and made several predictions that have since been confirmed by observations, most notably the specific pattern of temperature fluctuations in the CMB and the geometric flatness of the universe. It is considered by most cosmologists to be a well-established part of the history of the universe. But inflation has a startling consequence that its creator did not fully appreciate at first. In many versions of inflationary theory, inflation does not end everywhere at the same time. It ends in some regions, allowing those regions to cool down, form particles, and eventually form galaxies and stars. But in other regions, inflation continues, driving exponential expansion that creates ever more space. And within that ever-expanding space, new regions can stop inflating and form their own pocket universes, or bubble universes, each with its own Big Bang, its own particle physics, and potentially its own laws of nature. This is called eternal inflation, and it was developed extensively by physicist Andre Linde. In the eternal inflation scenario, the process of inflation never stops globally. Our observable universe is one bubble in an infinite foam of bubbles, each one a separate universe, and the foam is constantly growing, with new bubbles forming all the time. The space between the bubbles is inflating so rapidly that they can never come into contact with each other. They are forever isolated, forever unreachable, forever separate. And because each bubble may have different physical constants, different particle masses, different forces, the multiverse contains every possible variation of physics, from universes where atoms cannot form because the strong force is too weak, to universes where gravity is so strong that everything collapses into black holes immediately, to universes that are eerily similar to our own, but with tiny differences, to universes that are utterly alien and incomprehensible. The physicist Max Tegmark has classified these levels of multiverse into a hierarchy. At level 1, the multiverse is simply the infinite expanse of our own universe beyond the observable horizon. In an infinite universe with quantum fluctuations, every possible arrangement of matter occurs somewhere. This means there are, in the infinite reaches of space, exact copies of Earth, exact copies of you, reading exact copies of this sentence. The distances involved are staggeringly vast, far beyond the observable universe, but in an infinite universe, everything that can happen does happen somewhere. This is not mysticism. It is a straightforward consequence of probability in an infinite space. At level 2, the multiverse consists of the bubble universes of eternal inflation, each potentially with different physical constants. At level 3, the multiverse is the many worlds interpretation of quantum mechanics, proposed by Hugh Everett in 1957, in which every quantum measurement causes the universe to split into multiple branches, one for each possible outcome. In this interpretation, the universe is constantly branching, creating an exponentially growing tree of parallel realities. At level 4, the most speculative level, mathematician Max Tegmark proposed that every mathematically consistent structure exists as a physical universe. In this framework, our universe is one mathematical structure among an infinite ensemble, and the multiverse contains every possible universe that can be described by mathematics. Now, I want to be clear about something. The multiverse, at levels 2 through 4, is not observationally confirmed. We cannot see other bubble universes. We cannot communicate with other branches of the quantum many worlds tree. We cannot visit other mathematical structures. The multiverse remains, at this point, a theoretical prediction of well-established physics, particularly inflation and quantum mechanics, but it is not empirically proven. It may never be empirically provable, at least not directly, because the other universes may be fundamentally unreachable. But here is the connection to JWST and the size of the universe. JWST has confirmed one of the key predictions of inflation: the geometric flatness of the universe. The universe, as measured by the CMB and supported by JWST's observations, is flat to within the precision of our instruments. Flatness is a prediction of inflation. If inflation happened, eternal inflation is a natural, arguably unavoidable, consequence, and if eternal inflation is happening, the multiverse is real. So, JWST, by confirming the observational signatures of inflation, has indirectly strengthened the case for the multiverse. It has not proven it, but it has nudged the evidence in that direction. And if the multiverse is real, then the question, how big is the universe, takes on an entirely new meaning. Our universe, even if infinite, is just one bubble, one island, one room, in a structure that contains infinitely many universes, each potentially infinite in its own right. The total ensemble of reality, the multiverse, is not just big, it is not just infinite, it is an infinity of infinities, a structure so vast, so layered, so beyond the capacity of the human mind to grasp, that even our most powerful mathematical tools struggle to describe it. And then there is the string theory landscape, which takes this already impossible vastness and multiplies it again. String theory, one of the leading candidates for a theory of everything that would unify quantum mechanics and general relativity, posits that the fundamental constituents of matter are not point-like particles, but tiny, vibrating strings of energy. The properties of particles, their masses, charges, and interactions, are determined by the vibrational modes of these strings. But string theory also requires extra spatial dimensions beyond the 3 we experience, typically 6 or 7 additional dimensions, which are thought to be compactified, or curled up so small that we cannot detect them directly. The way these extra dimensions are compactified determines the physics of the resulting universe. And it turns out that there are an enormous number of ways to compactify 6 extra dimensions, an estimated 10 to the 500th power, 10 to the 500th power, different configurations. Each configuration yields a universe with different physical constants, different particle masses, different forces, different everything. 10 to the 500 is a number so large that it makes the number of atoms in the observable universe, about 10 to the 80, look like literally nothing in comparison. If eternal inflation populates each of these configurations in different bubble universes, then the multiverse contains 10 to the 500 different types of universe, each existing in potentially infinitely many copies. At this point, we have traveled so far from the question of how big is the universe that the original question seems almost quaint. We started with a beach, looking up at the stars. We traveled to the edge of the observable universe, 93 billion light-years away. We discovered that the total universe may be 100 sextillion times larger than the observable part. And then we discovered that this already incomprehensible universe may be just one of 10 to the 500 different types of universes in an infinitely vast multiverse. The scale of reality, if these theories are correct, is not just terrifying, it is an abyss, a limitless, bottomless abyss of space and time and possibility that swallows every attempt at comprehension and asks for more. And yet, here we are, on a tiny planet orbiting an average star in one arm of a spiral galaxy, in a corner of the observable universe, in one possible bubble, in one possible multiverse. Here we are, with our telescopes and our mathematics and our curiosity, looking outward, asking questions, trying to understand. And that, as we shall see, is perhaps the most remarkable thing of all. But before we get to the philosophical implications, there is one more terrifying topic we need to address. We have talked about how big the universe is. We have talked about what lies beyond what we can see. Now we need to talk about the end, the fate of the universe. How does it all finish? What happens to all those galaxies, all those stars, all those dark matter filaments? All that dark energy, all that space and time and matter. Does it go on forever? Does it collapse? Does it die? The answer, according to our best current understanding, is one of the most poignant and terrifying stories in all of science. The fate of the universe depends primarily on one thing: dark energy. Specifically, it depends on how dark energy behaves in the future. And there are several scenarios, each more unsettling than the last. The most likely scenario, based on our current best understanding, is called the Big Freeze, or heat death. In this scenario, dark energy is a cosmological constant, a fixed amount of energy inherent in every cubic meter of space. As space expands, more space is created, and with it, more dark energy. The expansion of the universe accelerates without limit, driving galaxies farther and farther apart. Within gravitationally bound systems like our local group of galaxies, which includes the Milky Way, the Andromeda Galaxy, and a few dozen smaller galaxies, gravity is strong enough to resist the expansion. But the galaxies beyond our local group will gradually recede, their light stretching to longer and longer wavelengths, as they move faster and faster away from us. About 2 trillion years from now, every galaxy beyond our local group will have receded past our cosmic horizon. Their light will be so stretched that it will be undetectable. A hypothetical astronomer in the far future, living in the galaxy that will form from the merger of the Milky Way and Andromeda, sometimes called Milkdromeda, who looks up at the night sky, will see only their own galaxy. Every other galaxy in the universe will have vanished beyond the cosmic horizon. There will be no evidence that the wider universe exists. No evidence of the Big Bang. No CMB, it will have been redshifted to completely undetectable wavelengths. No distant galaxies, just one galaxy, sitting alone in an apparently empty, static universe. All the evidence we currently have that the universe began in a Big Bang, that it is expanding, that it is filled with trillions of galaxies, all of that evidence will have been erased by the expansion itself. Any civilization that arises in that era will have no way of knowing the truth about the cosmos. They will live in profound, irrevocable ignorance of the universe's true nature, and they will never know what they are missing. Moving forward in time, the stars within Milkdromeda will gradually exhaust their nuclear fuel. The smallest, longest-lived stars, the red dwarfs, will continue to shine for trillions of years, far longer than the current age of the universe, but eventually even they will die. About 100 trillion years from now, the last star in the universe will burn out. The era of stars, the era that we currently live in, will be over. It will have lasted a tiny fraction of the universe's total lifespan, like a brief candle flame in an eternal night. What remains after the stars die is known as the degenerate era. The universe will be filled with the remnants of dead stars, white dwarfs, neutron stars, and black holes. White dwarfs, the cooling embers of stars like our Sun, will gradually radiate away their heat over trillions upon trillions of years, fading from white to yellow to red to brown to black, finally becoming invisible, frozen spheres of carbon and oxygen. Neutron stars, the ultra-dense remnants of massive stars, will similarly cool. But they are made of matter, and matter, as far as we know, is not eternal. Many theories in particle physics predict that protons, one of the fundamental building blocks of all ordinary matter, are not perfectly stable. They may have an incredibly long but finite half-life, perhaps around 10 to the 40 years. If proton decay is real, then over immense spans of time, every proton in every white dwarf, every neutron star, every planet, every rock, every atom of every kind will eventually decay, converting into lighter particles, positrons, pions, photons, neutrinos, which will gradually disperse into the void. All the ordinary matter in the universe will dissolve, atom by atom, over timescales so long that the current age of the universe is less than the blink of an eye in comparison. But even after proton decay, the universe is not empty. There are still black holes, and black holes are, in a sense, the final survivors. But even they are not immortal. In 1974, Stephen Hawking showed that black holes emit a faint radiation, now called Hawking radiation, caused by quantum effects near the event horizon. This radiation carries energy away from the black hole, causing it to slowly lose mass. The process is incredibly slow for large black holes. A black hole with the mass of our Sun would take about 10 to the 67 years to evaporate. A supermassive black hole, like the one at the center of the Milky Way, with a mass of about 4 million suns, would take about 10 to the 100th years. 10 to the 100. That is a 1 followed by 100 zeros. A Google years. After a Google years, the last supermassive black holes in the universe will evaporate in a final flicker of Hawking radiation, and then they too will be gone. What remains after the last black hole has evaporated? A cold, dark, expanding void. A universe filled with nothing but the most dilute possible soup of photons, neutrinos, electrons, and positrons, all moving farther and farther apart as space continues to expand. No structure, no complexity, no energy gradients to drive any process of any kind. The universe has reached maximum entropy, the state of maximum disorder, where nothing can happen, nothing will happen, and nothing ever will happen again. This is the heat death of the universe, and it lasts forever. Not for 1 billion years, or 1 trillion years, or a Google years, forever. An eternity of cold, dark, empty nothing. The universe does not end with a bang. It ends with a whisper, and then silence. Eternal, unbreakable silence. I want you to sit with that for a moment. Everything that exists, every galaxy, every star, every planet, every person, every thought, every poem, every symphony, every act of love, every act of courage, everything that has ever mattered to anyone who has ever lived, all of it was a brief flicker of complexity in an eternal desert of entropy. A momentary eddy in an infinite stream. A pattern that arose from randomness, persisted for a cosmic instant, and then dissolved back into randomness. That is the Big Freeze. That is the most likely fate of the universe. And it is, in its own quiet way, the most terrifying thing in this entire video. But there is a scenario that is even more dramatic, even more violent, even more final. It is called the Big Rip, and it is the scenario that becomes possible if dark energy is not constant but is growing stronger over time. Remember the hints from DESI and the Dark Energy Survey that dark energy might be evolving. If dark energy is getting stronger, the expansion of the universe is not just accelerating but accelerating at an ever-increasing rate. And if this trend continues without limit, eventually the expansion will become so powerful that it will overcome every force in nature. In the Big Rip scenario, here's what happens. Billions of years from now, the expansion becomes strong enough to tear apart galaxy clusters. Galaxies that were gravitationally bound together are pulled apart by the stretching of space. Then, the expansion becomes strong enough to tear apart individual galaxies. Stars that were orbiting in the gravitational embrace of their galaxy are flung outward as the space between them expands faster than gravity can hold them. Then, solar systems are torn apart. Planets are ripped away from their parent stars. Then, planets themselves are torn apart. The rock and iron and silicate that make up a world like Earth are pulled apart by the expansion of space within them. Then, atoms are torn apart. The electromagnetic force that holds electrons in orbit around nuclei is overcome by the expansion. Then, atomic nuclei are torn apart. The strong nuclear force, the strongest force in nature, is overcome. Protons and neutrons are separated. And then, in the final instant, space-time itself is torn apart. The fabric of reality rips. Everything that exists, every particle, every point of space, every moment of time, is annihilated in a catastrophic rending of existence. The timeline for the Big Rip depends on how quickly dark energy is growing. Some models suggest it could happen as soon as 22 billion years from now. That is about 1.5 times the current age of the universe. In the grand scheme of things, that is not very long. If the Big Rip is real, the universe is not just going to die a quiet death. It is going to be murdered, ripped apart at the seams. Every atom, every bond, every structure, every memory, every possibility, destroyed in a final paroxysm of expansion. It is the most violent ending imaginable for the cosmos. There is a third scenario, less likely given current evidence but not impossible, the Big Crunch. In this scenario, dark energy either weakens or reverses over time, allowing gravity to eventually halt the expansion of the universe and pull everything back together. The universe would begin to contract, slowly at first, then faster and faster. Galaxies would begin to approach each other instead of receding. The CMB would blue shift, becoming hotter and hotter. Eventually, the entire universe would collapse back into a single, infinitely dense point. A reverse Big Bang, a cosmic implosion. Some theorists have speculated that such a crunch could trigger a new Big Bang, giving birth to a new universe in an endless cycle of expansion and contraction. This is the Big Bounce, or the cyclic universe model. In this view, the universe has no beginning and no end. It has always existed, cycling through infinite iterations of birth, expansion, contraction, and rebirth. Each cycle could produce a universe with different physical constants, different particles, different laws. Our universe would be just one cycle in an infinite chain, one heartbeat of an eternal cosmic pulse. The idea is beautiful in its way. It offers a universe that is eternal, that never truly dies, that always resurrects itself in a new form. But current evidence, particularly the observation that the expansion is accelerating, makes the Big Crunch scenario unlikely. For the universe to recollapse, dark energy would need to not only stop growing, but reverse its direction, becoming a force of attraction rather than repulsion. While this is not impossible, there is no observational evidence for it, and most theoretical models do not predict it. There is one more scenario worth mentioning, proposed by the great physicist Roger Penrose. Penrose's conformal cyclic cosmology, or CCC, proposes that the death of the universe in the Big Freeze does not need to be the end. Penrose argues that when the universe reaches a state of maximum entropy, with nothing left but photons and other massless particles, the concept of scale becomes meaningless. In a universe containing only massless particles, there is no way to define distances or time intervals. The incredibly diffuse, cold, empty universe at the end of time becomes, in a sense, mathematically identical to the incredibly hot, dense, uniform universe at the beginning of a new Big Bang. The end of one aeon is the beginning of the next. The universe dies and is reborn, not through a physical crunch and bounce, but through a mathematical transformation, a conformal rescaling, in which the infinite future of one universe becomes the initial conditions of the next. It is a deeply elegant, deeply strange idea, and Penrose has even claimed to have found evidence for it in circular patterns in the CMB that could be the echoes of events in a previous aeon. What does JWST tell us about the fate of the universe? JWST's confirmation of the Hubble tension suggests that the universe is expanding faster than our models predict, which is consistent with the Big Freeze scenario and potentially with the Big Rip scenario if dark energy is growing. JWST's dark matter map helps us understand the gravitational dynamics of the cosmic web, which will determine how structures dissolve as the expansion accelerates. And JWST's observations of early galaxies help us understand the history of structure formation, which in turn helps us model how that structure will come apart. The bottom line is this: the most likely fate of the universe, based on everything we currently know, is the Big Freeze. The universe will continue expanding, the galaxies will drift apart, the stars will die, matter will decay, black holes will evaporate, and the cosmos will settle into an eternal, cold, dark, silent emptiness. It is not a dramatic ending, it is a slow fade, a long, quiet goodbye. And in its own way, it is more terrifying than any explosion or rip or crunch, because it is so gentle, so gradual, so relentless, and so final. Now, having traveled this incredible journey, from the first humans looking up at the night sky to the most powerful telescope ever built, from the most distant galaxy ever seen to the theoretical multiverse, from the beginning of time to its end, I want to talk about what all of this means. Not scientifically, philosophically, emotionally, existentially. What does it mean to be a human being, alive right now, in a universe this large, this old, this mysterious, and this doomed?